Instantiations. I'm not sure this talk will be as inspirational as the last one, which I thought was really great. And it's cryptography, and we're getting hungry, so the odds are stacked against me. But we'll continue. So today I'm going to talk about security, kind of what we offer in VA Smalltalk, what was there, what's there now, where are we going with it, why is it important. So this is kind of what we'll go through, just a quick kind of security overview of all this. Some architectural goals of what we've been trying to do. New exciting kind of upcoming release of OpenSSL 1.1, and this is the library that we use to get the cryptography and SSL TLS support in our product. And so we'll talk about the cryptography library, which is relatively new, and the SSL TLS library, which is older, but we've revamped in recent times. So first, why is this important? And I think in today's world, it's just really not going to be hard for everybody to grasp. Secure communications is difficult. We've seen this, even cryptographers get it wrong, people whose business it is to do this. We've seen this at the protocol level, such as SSL, which is now broken. We've, if anybody knows about Microsoft's point-to-point tunneling protocol, it's like the poster child for a broken protocol. We also see problems at the implementation level. Which is a little different. Protocols, once those break, everybody's implementation is wrong, who faithfully follows the protocol. And so those are pretty terrible. But we also see implementation breakage. In fact, we see it in OpenSSL, perhaps considered by many to be one of the worst security vulnerabilities since digital communications began, and that is the heartbleed bug. Does everybody know heartbleed? Raise your hands. Yes. So that was a buffer overrun, bounce check missing, came in 2012, picked up, noticed in 2014, grabbed about 65,000 bytes or so of just stuff, people's keys, secure cookies. It was pretty terrible. And finally, even if you get all that right, protocol, your implementation is spot on, all your test vectors pass, everything's perfect, you still have the problem of these algorithms as they're expressed on digital machines, which is different from expressing them on a whiteboard, which is that CPU, observations of the CPU, observations of the cache, timing attacks, so various of these things about how they run can give you insight about the inputs. And these are what are called side channel attacks. And so the bottom line is, in any cryptography course, if you've ever taken any, the rule number one always starts the same way, and that is never roll your own crypto. And these are the reasons why. So it's important to use, and that's one of the reasons we don't try to implement our own cryptography. We try to use external ones like OpenSSL, libsodium, the NACL guys is another excellent one. And because it's just hard. It's really, really hard. Demand for secure communications, obviously that's going one direction. And our customers have seen this recently. They get a lot of pressure from their customers to provide higher security applications. Normally we think of this as just a connection, like a TLS connection, but there's lots of more use cases for this, and that leads to kind of what we've exposed with the cryptography library. So what did we have? Well, before 8.6.2, we did have an OpenSSL binding. It was quite old. The only good thing that can be said about it was that it predated Heartbleed by about a decade. So a good marketer could actually turn that into something good. And we had no cryptography primitives. So the crypto library, incidentally, is a bunch of the cryptographic primitives that are brought together to implement protocols like SSL and TLS. But separately, they have value that we'll talk about. There was minimal help, so this is a native binding, and native bindings can present a lot of complexity to the Smalltalk user because essentially it can become like programming in C. some of the issues there, and we don't want to deal with that as small talkers. So I'll talk about how we help in those cases. Lastly, there were not a lot of test cases, just a handful, just to show you could bring up a connection. 8.6.2, this all changed. We completely revamped everything. We brought official support to the 1.0 branch of OpenSSL, which is basically the current stable branch. There's been 3 versions in the 1.0 series. We support them all. We've got a native memory manager I will talk to you about that's written in Smalltalk. We introduced the cryptographic library with all the primitives, enhanced SSL, TLS, and a lot of testing. A lot of tests. So we grabbed official test vectors from all specifications of these protocols to show that by nature of us binding to OpenSSL, we were not changing the situation and creating security vulnerabilities. Finally, we have, and this stuff's not always obvious how to use it, and one of my favorite ways to learn things is to have live coding examples, which is what we provide. I don't like reading API documents. I like to just, I think a lot of small talkers are the same. They like to browse around, look at how things are used. Well, the story-driven examples we have give you a place to do that and to figure out how, give some common use cases. Coming up in 8.6.3, we're going to have OpenSSL 1.1, which is a big overhaul post-Heartbleed response. They've done a lot of great work. It's the only GitHub repository I follow daily. And just over the past year and a half of the kind of changes that have been made on that project are pretty remarkable. And in doing so, we continue support for 1.0 and everything there, and trying to deal with the API breakage has been an interesting piece, but we've managed to do it. There's a lot of new cryptographic algorithms we expose. Authenticated encryption, if anybody uses symmetric ciphers, shared key type of stuff, everybody should be using authenticated versions of that today. We have new key derivation schemes, which, if anyone's heard of LastPass, 1Password, Dashlane, KeyPass, these are the algorithms that are used in those products. So you can actually, 1Password is actually a good example. They expose their complete internals. You can completely write a 1Password read and writer in VA Smalltalk. It's got all the components there. Finally, the secure memory module, which is really intended for long-running servers, it's going to protect, help protect in-memory keys or sensitive data. This is using something like this would have helped with Heartbleed, for example, and so we'll talk about that. Just some architectural goals, just touch on compatibility, introducing the new crypto layer. This was slid underneath the existing SSL TLS layer. So there was a lot of compatibility that had to be handled there to make sure we weren't breaking our customers. And so we've added, like I said, added support for 1.1. And however, the differences between all these versions now should be in large transparent, except for algorithms. Obviously, if you use new algorithms, we don't backport those to previous versions. Fairly obvious about separation of concerns as a good goal to have, but just to make a point that we separate our dispatching engine. This is the piece of the product that will actually perform calls to OpenSSL, handle error conditions. This is separate from the API objects, which only the user is exposed to, and they don't have to worry about those details. Finally, there's a native memory manager written in Smalltalk. It is specifically designed for OpenSSL and the semantics of the types of memory they return, from static memory that we're not supposed to free. I've seen plenty of support cases on that. Reference counted memory from OpenSSL, as well as just unmanaged memory that you're supposed to free. This is all handled. You don't have to worry about freeing your memory, or if you do, if you're going to accidentally double free it or whatnot. So we have GC help in case you forget to actually free your native memory. Especially with cryptography, this isn't preferred, because typically this is sensitive information. You don't want it to hang around too long, but in the case that you do, it will be cleaned up. In typical applications, that'll happen pretty quickly. From a theoretical standpoint, finalization of the garbage collector could extend out to infinity, but you've got to have some serious CPU stuff going on for that to actually happen. Performance, all our OpenSSL calls are made on native threads. So this will block the calling Smalltalk process, and then other processes may continue. And so, I've had crypto flows I've created where I can push 6, 7 threads of execution at once. The older version required us, the user, to implement thread locking for this level of concurrency. We have that. Thankfully, 1.1 did away with that. They implement it internally. Our product detects that and doesn't try to plug things in if that's the case. Finally, safety. As I said, the native memory manager, we just kind of covered this. There's different types of memory OpenSSL is returning. The native manager is classifying them as appropriate and handling, what it means for who owns the memory. And so it's got its own internal reference counter and handles this for you to keep kind of the details of C away from you. So OpenSSL 1.1, major revamp, as I said. Post-Heartbleed, good news is accreditation process, FIPS 140-2 is now sponsored, so that'll be moving forward. John touched upon today, I think a little bit, that it's still in beta. We certainly hope by our release at Q4 that it goes, that it's released. But so we just keep up with the betas as they come out. So with all this new algorithms, this is all great. The bad, API breakage, we hate that. So in order to handle it, we do a few things. The first is we've got version adapting memory layout. So as a binding is made to a specific DLL, that version is detected, rummages through all the binding, the wrappers, they reconfigure their memory layout for that specific version of OpenSSL. Incidentally, in 1.1, most everything went opaque, so they provide getters and setters. However, so now you can think, well, what if I use those getters and setters, but now I go back to version 1.0, do I have to change my code? No, you don't. So everywhere we're providing new capability, we are also implementing, for older versions, fallback code, and typically we use the direct implementation as it's described in OpenSSL. So we'll do this for everything except, as I keep coming back to, algorithms. We're not going to backport algorithms, and the reason touches upon the side channel attacks. The behavior in a VM exercising these algorithms is hard to predict in terms of what you're actually exposing and what's actually observable. The last point touches on how careful you actually need to be. So imagine that you're verifying a user's password against, so it creates a hash, you're comparing against a hash, and you use Smalltalk equals. You have just exposed a huge security vulnerability because that is a short-circuiting thing, as you would want it to be for performance reasons. But the adversary can just submit n number of queries to actually use timing attacks to figure out what that key actually is, or hash. So you have to use special versions that take the same amount of time for any query, no matter how close or far away it is from being equal.
Sorry, next question, I didn't forget, so what's the problem with the timing?
Timing attacks? So if the first character of your 50 is different, then the time it takes to establish as it equals will be vastly different than if they're all equal except for the very last character. So because the first one you can establish it's not equal, I'm out of here. But if they're all equal except for the very last, then you have to loop, chewing up time, observable time, loop, and then the very last one is not equal. That's a different amount of time that it took to do the first one.
And this gives an indication about...
That gives an indication about, yeah, you can use that to actually reverse engineer the key. That's right. So the crypto library has a bunch of stuff to it. One is the secure memory. We're going to just kind of breeze through these. We'll just go through. So the secure memory one's kind of neat. This is for long-running servers, again, Heartbleed. This would have stopped a Heartbleed if folks put all their secure stuff inside, classified as secure memory. It's intended for long-running servers, and we have a secure object. You can kind of think of it as an unmanaged byte array of sorts, stored in unmanaged heap. Typically, you don't want to store keys and things in managed memory because the garbage collector is creating copies of it. So even if you zero it out, you're just zeroing out a copy of it. So the strategy for Linux and Unix is to use OpenSSL 1.1's new secure arenas. So there's a special section of heap that is pinned to RAM. It's page guarded on either side. It's from wandering pointers coming in from either side. If they hit those, it'll segfault. That will terminate the application. It's also prevented from showing up in core dumps on all the platforms we support. And so that's something that you want to use for your secure keys. You keep it in that section. And what do we do on Windows? Well, OpenSSL 1.1 doesn't provide secure arenas for Windows yet. Yet we still wanted to do something. So what we did was say, okay, well, our strategy for Windows is, let's limit the amount of time that sensitive data will be observable in its decrypted form. And so we'll assume this thing can page to disk. We'll assume that core dumps are unavoidable. And so it doesn't actually need any sort of special section of the heap that it lives in. It's just normal heap memory. So to do this, we use Microsoft's Crypto API. The encryption key is generated on boot. It is per user. It is stored in kernel memory in a non-pageable section of it, so it won't show up on disk. And by default, you can change this, but only the Smalltalk process can decrypt it. You can set it up so cross processes can also decrypt it. And what we had to do here was for the dispatcher, the guy that actually makes OpenSSL calls, we had to make sure that incoming arguments that were encrypted, we decrypt them, quickly make the call, encrypt it back. Interesting stories I found out one day. That works well until the call was free. And if you free the memory, you don't want to encrypt it back, as I found out one day. But that's been fixed. Okay, so as far as our cryptographic library, we have these really high-performance I/O streams that that OpenSSL implements, but we expose the bindings for. So you can actually pipeline these things together, and I'll show you that there's an example here at the bottom. It's a long sentence, but let's see if we can work it through. We're going to perform buffered writes of base 64 encoded encrypted data to a file. So what does this look like expressed as a bio stream? So we have a buffer bio, which we're going to write to. Then that's the actual symbol used in Smalltalk, to like a pipe, but it's the OR symbol. That's going to go into a SHA-512 bio, which is going to pass it right through, but it's going to calculate up a hash value as information flows through. Goes into the AES-256 symmetric encryption, and that will encrypt it. So now what comes out of here is ciphertext. That will base 64 encode the ciphertext, which goes into the file bio, which will then write that out to a file. Now to reverse this, it's fairly easy. Instead of doing a write, you do a read. You read from here, which will request buffer data from SHA-512, which in turn, you can see how it goes all the way down till you get to file, and it's pulling information out, base 64 decoding it, decrypting it, SHA-512 hash in a decrypted plaintext, buffered, read. And you can set up a lot of Smalltalk processes with these pipelines and get really high performance throughput on crypto streams. Quick overview of the library. The message digest, these are secure one-way hash functions. By secure, we mean collision resistant. If you find collisions, that's terribly bad. So algorithms we have, MD5 has known collisions at this point. The SHA family, we got Whirlpool, which is kind of a patent-free type of deal. 512 byte. And the new one for OpenSSL 1.1 is Blake 2, really, really, really fast. Two variants, one is really good for 32-bit machines, one is really good for 64-bit machines. So you can see here the way you create a digest just quickly is, there's your API object, digest, kind of a factory method, SHA-512, ask for a printable digest on Hello World, and you get this. We have MACs. These are keyed hash functions to just add authenticity to data integrity of the message digest. So new algorithm for CMAC is used a lot in credit card companies and things of this nature. This is a MAC backed by cipher, CDC cipher. HMAC is backed by a digest. It's almost the same way you use things. It's an API object. Asking for SHA-1, and you say HMAC printable digest, but now you're adding this secret key along with it, which provides your authenticity. Symmetric ciphers, this has had a lot of work done to it. So this is encryption for confidentiality, shared key. So this assumes that Alice and Bob have already had an opportunity to come to a consensus about what the key is. So we have block ciphers, tons of them. Yes.
Yeah, just one question, like to understand better, like what does it mean, like confidentiality? What's the difference between what we got now and the previous one? So this is not confidentiality, right?
The MACs do not provide confidentiality. They do not provide encryption guarantees. In fact, there's nothing about a MAC that in a digest that says that information about the plain text can't be part of a digest output. So there aren't confidentiality guarantees for MACs or digest. This is really about, can you modify, as an adversary, can you modify the data en route or wherever and be able to detect that? With hash functions you can't, but with MACs you can. So MACs are actually used to add authenticity to the old style of symmetric ciphers that were unauthenticated. And these are like, if you've ever heard of AES-CBC, this only assumes that an attacker is passive. He can only listen, but he can't modify it. He can just listen. And
confidentiality, the encryption for confidentiality means that I cannot modify something that's been encrypted.
No, you cannot decrypt.
Because you can't decrypt.
Yeah.
Yeah. And so, so some of the modes we see here are, CBC, a lot of modes. XDS is a new one that came in, that's disk encryption. It's a little better than unauthenticated, but authenticated encryption requires additional data for the authentication tag. Disk encryption, you don't have additional space, so it does some different stuff. Authenticated modes, this is what everybody should be using today. There's really no reason. In the past, people took unauthenticated modes and applied a MAC to it, one of the MAC algorithms for authenticity. That was done terribly wrong in the past by different protocols. IPsec was the only one that got it right, which is you encrypt the ciphertext and you MAC the ciphertext. But here, so around 2010, this became such a bad problem that the crypto folks came up with authenticated modes that will do this for you. And so that's what GCM, CCM, OCB in 1.1, extremely fast as any of the unauthenticated forms, as from my trials have shown, so just use one of those. Stream ciphers, Cha-Cha-20, this is for those who know, like the NACL library. Forget the cryptologist's name, Daniel Bernstein, I think that's his name. Famous guy, came up with these great algorithms. So this is a streaming cipher. Small example, probably running out of time, so I'll just breeze through that. Here's an encrypt, decrypt. We kind of create a unified API for unauthenticated and authenticated. Just notice that authenticated means at the end of the encryption, you need to keep the tag data. Because when you decrypt, you're gonna need it, because the adversary may have modified it somewhere. And so now when you decrypt, you want to be sure you don't decrypt modified ciphertext.
So what does it mean, ID?
So ID is, well, it's really two things. It's either initialization vector, kind of like your starting point that gets mixed into block ciphers, for example, it's the initial thing that gets mixed in with the first block's XOR deal, and then it does a series of rounds. There's also nonce as another interpretation for different ciphers. That means the number can only be used once, but it doesn't have to be indistinguishable from random. So IVs need to be indistinguishable from random. And so that's the difference. You'll have to look at the different modes and say, and that's another source of problems sometimes. In fact, we've seen it in TLS, where the IV was not indistinguishable from random because they used something from the previous packet. I forget if that's Beast or Crime Attack, I can't remember which, but that's another big area that you gotta get right. So public-private key, so there's so many algorithms for public-private key that it's really hard to go over, but just key exchange. The important thing here is it's an order of magnitude slower than symmetric ciphers. These are often called asymmetric ciphers. So they're typically used just for like session setup. Like we need to come to an agreement about a shared key. This is the way we do it. And then after that, we're going to switch and use the faster symmetric ciphers. Okay, key derivation, this is new. Like I said, you use one password. If you use LastPass, dash lane, or key pass, these are the algorithms that they use. So HKDF is actually a little different. This expects a high entropy key, but which is high level of randomness, but then can produce from it, it can derive n number of keys, other keys that you can use, or it can key stretch, so it can make a small key and turn it into a big key. And there's lots of applications for this. The next two are the ones we're probably familiar with from these applications, which is the input is expected to be low entropy, like a human made up password. It doesn't matter what you do, it's cryptographically weak. And what it's going to do is it's going to, basically it's intentionally slow, okay, for brute force purposes. So this algorithm needs to run fast, because you're going to tune it to maybe take a second. And that way, somebody brute forcing against it is going to be slowed down tremendously when they try to actually do this. So PBKDF2 is password-based encryption. It is CPU hard, so it's designed to really be hard against the CPU and take a long time computationally. Scrypt is an even better one. It was in response to folks going out and buy, with their $5,000 and buying custom ASIC boards, burning these algorithms on, and launching 300,000 rounds per second against these. So they said, okay, well, let's create a new algorithm that's not only CPU hard, but it's memory hard too. So you can make this algorithm take up to a gigabyte to actually do a key derivation, and that keeps it away from custom ASICs or GPUs. And that's another option we have now for OpenSSL 1.1. So here's an example of Scrypt, where you basically specify a key length and you derive from a password, a low entropy password, and you want to turn it into something strong. And this would be like a thing you would store in a database. So you don't want to store the password in the database, you want to store cryptographically strong hash. But then along with that comes a lot of parameters. And you can see these parameters, they're really quite difficult to come to consensus on your own. These are fine-tuned memory CPU parameters. I didn't really like that. OpenSSL didn't offer anything different. So I went to the libsodium library and said, oh, well, they have Scrypt and they offer two knobs, one for CPU, one for memory, and they derive the rest of these values. So I borrowed that logic, and that's what you can use instead. Now when you want to arrayify it though, so now you've got this thing in the database, you bring it back, somebody's asking, is this the right password? You've got to have all these parameters. You run it, it's going to be, again, it's going to be slow, so you can imagine an attacker can only ask this question so many times per second. And here's another point about the verification routine here. Don't use equals. So that's something, usually I try to stay away from any of this algorithm stuff, but here in the verify routine, I did have to make sure that I used OpenSSL memcompare so that we get constant time comparisons against the hashes. So this is the last slide. And the reason it's so short, I mean, SSL, TLS has moved forward considerably, but it's now built on the crypto library, so it's inherited everything we've really just talked about, including the native memory manager and things of that nature. So just in terms of its features, it's 1.2 TLS. There's some X509 stuff we have, and the OpenSSL 1.1 compatible, of course, at this point. And that is the end. Is that the end of my presentation? Oh, I went the wrong way. Yes, that is the end of my presentation. Thank you very much. Any questions?
Seth,
What?
could you go back to so this question is just to get a better idea of how paranoid should we behave as parameters. So for instance, this verify with receives the password as an admin. Does it also, once the comparison is finished, replace the chapters with null, for instance, or something in the argument that it receives?
Yeah, so what it's going to do with that verify is going to take that low entropy key material and it's going to run Scrypt against it. So that's going to take a chunk of time. That's going to return a hash value that's very large and cryptographically strong, and it's going to compare it against. We'll pretend that p hash is what you have sitting in your database. That's the thing that.
No,
okay.
my question was, that method receives the password, the actual password.
Yes.
And after the
Oh.
comparison, should it also replace every character in the argument?
I see. So the bad thing here is that I showed a literal string for just basically to make it easier to show, but I would never, ever use a literal string. In fact, I wouldn't even use a Smalltalk heap object at all. I would use a unmanaged object that can be freed and you can zero out. So that's what we do, we zero out the memory.
Okay.
Unmanaged memory. Zeroing out Smalltalk memory doesn't do much because it's in the scavenge or compaction or mark and sweep, free list adding, there's copies of these things made. And so you're just zeroing out one instance of it. And like I said, I mean, at the end of the day, it's all about what is your threat model. If your threat model does, it's not like you're doing it wrong. If your threat model doesn't include some of the stuff we talked about with the secure memory, that for some folks that just, use a key that's from a Smalltalk heap. It really is up to you to define how strong you want to be, what you have to protect against. So I don't want to ever phrase it like you're doing it wrong if you use, it's really just define your threat model first, and these are some extra mechanisms to accommodate.
Very nice presentation, thank you. Just a comment to the question. Security or cryptography alone is not the answer. You want to provide security in depth, right? So your application is not the only thing that, if you ask how paranoid I want to be, exactly as Seth said, it depends on your threat model, right? If it's, you can never be paranoid enough almost, but if you really have mission critical applications, you want additional security infrastructure around that. So you mitigate the risk of your adversary coming down to your memory or whatever.
Good point, thank you. Neil?
Obviously I see 100% where every course is coming from in saying don't roll your own. Even though they have a motive for saying that, but it couldn't be more true. This is hard. What is the attitude to rolling your own in addition? Is the attitude that if you put your own crypto on top of, inside the proper stuff, that's an additional surprise, or is the attitude that no, you could actually weaken the cryptographic strength under the impression of doing it right?
Yeah. Well, in every course that I've taken on it, the attitude is that it takes a long time to verify the correctness, and we've seen what correctness means so many different things in crypto land that it's typically discouraged. But I'm not a cryptologist or cryptographer, so I can't say.
I was just wondering what their attitude was to the surprise factor of someone who maybe did encrypt using a really hard algorithm and then encrypted what they gave to it in their own wonderful way. Whether that was
So the problem is, well, it's a good point. That's another thing you hear in classes.
Is there any way it could be bad?
Yeah, I mean, there are ways it could be, and the problem is that sometimes folks use cryptographic primitives like Lego blocks. Like you can just stack things one on top of the other, and that just adds security, and that's not true. It could go the other direction.
Yeah, exactly.
so
That's
yeah.
the point of my question.
Yeah.
I think
It can be bad.
Yeah.
I think what you're going to have there is, at best, it's going to be security by obscurity is what you're adding to it, and at worst, you're going to make the real algorithm wake up.
But this is the danger.
You can make it wake up, or you can just add a bit of obscurity.
Yeah.
But the problem is, yeah, I can observe your machine, the way that it's running these algorithms on a digital machine. I can observe those in ways that are independent of whether I see your source code or not.
Yeah.
So, yeah.
Just to all of these discussions, I wanted to add a very general comment. It has been known in history that there is only one known enciphering technology which has not been cracked. This is the one like that created by physical devices on paper tape. And still, you could steal the paper tape, copy it, and put it back. People who have analyzed historical situations, like Hans Rohrbach, who worked in the Second World War, in the foreign ministry of Germany, published in 1948 that the German foreign minister could read everything from every other country.
Yeah.
And I met him in the 70s or 80s, and he said, you can be absolutely sure that every encrypted system can be unpurposely deciphered.
Yeah.
It's only a matter of effort.
Yeah, and computing power as we continue. You always have to stay ahead of the curve, and yeah, one-time pad. Problem with that is your key has to be at least as large as the message, so now that's kind of a problem. But it's kind of a fascinating field. I mean, as you were talking about, you can go back further to the Caesar cipher and look at how things have changed all the way up to the digital age. It's a fascinating field. But anyway, time for lunch, I guess.